And share screen, go there and there and here. Okay. All right. So the quiz, it's now too late to turn in a quiz. So, and another reason why it's a hard deadline is I'm going to go over it. I mean, it wouldn't make sense for me to let you turn it in later after I go over it, right? Okay. But in case you're wondering, how do they derive the formula for the volume of a cone or the volume of a sphere? They do it by this, by a volume of a solid revolution. Okay. They didn't come out that hard, I don't think. Most of you got it okay. And the key thing to remember when you're integrating is R and H are constants. And over here, R is a constant, right? Okay, so for the actual work, you're just integrating pi r squared. So integral from 0 to h, integral from 0 to h of pi r over hx quantity squared dx. Okay, take out the pi. R squared over h squared being constant, that gets to come outside. So pi r squared over h squared, integral of x squared dx from 0 to h. So pi r squared h squared is constant, just leave it outside, and that's fine. Okay. And then I integrate x squared, and that gives me x cubed over 3 from 0 to h. Again, very convenient. When you plug in 0, you get 0. So I just plug in h. So pi r squared over h squared, h cubed over 3 minus nothing. And I decided not to write the minus nothing. You know it's there, but there we go. H cubed, h squared cancels, leaving me with an h. So 1/3 pi r squared h. And you might remember from maybe 6th grade geometry or something like that, that's the formula for the volume of a cone. You might say, how did they get that? This is how. Right? If you take this triangle, right, and spin it about the x-axis, do you see that cone? With a radius of r and a height of h. Okay? So that's how they derive the formula for the volume of a cone. Okay? And likewise for the volume of a sphere, you may have heard 4/3 pi r cubed. So how do you come up with that formula, 4/3 pi r cubed? You take, well, you could say the unit circle, x squared plus y squared equals r squared. If you solve for y, you get that. This is the top part. Spin it about the x-axis, you get a sphere, right? A volume of a solid revolution. Okay. Now, you could integrate from negative r to r, but it was a lot easier, and a lot of you noticed that. Because of symmetry, I'll just integrate from 0 to r and double my answer, right? So I'll just go from 0 to r. So pi y squared, pi times the radius squared. Very conveniently, if you have a square root squared, you just drop that off. So pi comes out. And instead of going from negative r to r, I go from 0 to r and double it. So 2 times the integral from 0 to r of r squared minus x squared dx. Okay. And you have to keep in mind, r squared is a constant. So don't go r cubed over 3. Okay. You are going to go x cubed over 3 dx. Okay. And one other function about the dx, say, why do I have to write the dx? Yeah, I admit sometimes it seems like it's meaningless, but if you have more than one variable, it is crucial. Okay. This tells you what the variable is. For instance, suppose this said dr. Suppose it said r squared minus x squared dr. Then all of a sudden, r would be the variable and x would be the constant. And then you have to treat x or x squared as a constant, right? But like this, dx, that tells me x is the variable, that's constant. Okay, so 2 pi, integral of r squared is r squared x. Integral of x squared is x cubed over 3 from 0 to r. Again, when you plug in 0, you get 0. Plug in r. R squared times r is r cubed minus r cubed over 3. R cubed over 3 minus r cubed minus r cubed over 3 is 2r cubed over 3. That's like 3 over 3, right? So 3r cubed minus r cubed, 2r cubed, multiply it all together. 4/3 pi r cubed, which you might recall is the formula for the volume of a sphere. Okay, so now, if you ever wondered back when you first saw the formula, I don't know, 6th grade, 7th grade, here's the formula for the volume of a sphere, 4/3 pi r cubed. Here's how to find the volume of a cone, 1/3 pi r squared h. And you say, how did they come up with that formula? this is how they come up with it. And you derived it yourself, which is good. Of course, you know what you were aiming for. I mean, I already gave you the answer, but, you know, in case you ever wonder, how do they come up with these formulas? This is a way, with the volume of a solid revolution. Okay, so I just want to give you that, and that's that. And now we're ready to move on. Okay, so I'm going to go on to 6.4 and hopefully 6.5. Now, if everything goes according to plan, I think I can actually finish 6.5, all of this by today. Okay, and now I'm not going to move up the test. The test is still going to be next Tuesday. So if that's the case, I'll just get started with chapter 7 on Thursday. We're not going to sit around and do nothing. I'll just go ahead. But I already said the test is next Tuesday. I'm not going to change it. So if I happen to finish early, that's fine and dandy. In which case, you know, I'll just go on. And even on the test day next Tuesday, I'll start off with lecture, and the second half will be the exam. Okay? And by the way, I'm not going to give you guys a quiz on Thursday. I've been giving you quizzes the first 2 weeks, but since you have a test next Tuesday, I decided, okay, no quiz this week. You're focusing on the test. Okay, remember, you can come up with a cheat sheet, 8.5 by 11 sheet of paper like this, okay, front and back. Put any formulas that you wish on one sheet of paper, but other than that, you can't use your book or your homework or any other notes. And of course, you can't use people or the internet. You can't use your computer. You can use your calculator. You can only use your cell phone just to take a picture of the questions, right? So click for the questions that I'll show you and go from there. Okay. In fact, maybe I can even show you an example. Let me see if I can find something. No, maybe not. Oh, well. Yeah, this works. It looks something like this. Okay, this obviously doesn't apply to us. Of course, I'm not going to show you our actual test. It says name, row, and seat. Ignore that. That was if we had met on campus. I want to know where you're sitting, what row, what seat, but that doesn't apply now. Okay, and see, this test has 10 questions, I suppose. So you might have to split it into 2. Okay, well, you don't really have to take a picture of that or that. Okay, so maybe I'll just go like that. So I'll say, okay, everybody get your cell phones out now. I'll give you 15 seconds, take a picture of this. And then I'll scroll down and, okay, give you another 15 seconds to take a picture of that. And then you got it, and that's it. And that's how I would show you the test, okay? All right, so we're back to work, problems involving work. Okay, so I'll just go back and do a lot more. 6.4, number 7, please. Okay, so 6.4, number 7. Give that to you. And maybe once again, I'll show it to you if you need it. Okay, problem 1, problem 3. Whoops, can't see all of problem 3. That's the best I can do for now. And then the next page, some there. Oh, that focus is pretty good. And maybe there if you need it. So that's up to problem 21-ish. And some more there. And there. Okay. Do we have anything on the next page? No, we don't. Okay, so that's that. And I'll tell you what, since I got the book, why don't I just give you 6.5. 6.5. Okay, 6.5 is a much easier section in my opinion. It's called the average value of a function. Average value. The formula is here. I'll give that to you. If you want to put that on your cheat sheet, you may. If you can't read it, it says F average, AVE. Although I like to say AVG for average. AVE to me sounds like avenue, but anyway. So there's the formula. You can put it on your cheat sheet if you want. Okay, 6.5. Let's see. We had to go 1 through 17. Okay, so here's the top there. Try to aim it right so you can see it. And a little bit farther down. And there's some graphs at the bottom there. So there's that. Oops. Try to aim it right. Okay, so you can just replay the video as many times as you want, go forward or backward as necessary. Okay. All right, so I was going to go back and do 6.4, number 7. A force of 10 newtons, force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. How much work is done in stretching it from its natural length to 6 inches beyond its natural length? Okay, so obviously we're not doing metric here. We're doing English system. And English system, it's pounds and feet. Now, they give it to me in inches, so I have to convert it to feet. So what is 4 inches? 1/3 of a foot. 6 inches, half a foot. Right? Okay, so I got all the key ingredients here. So we know 10 pounds for 4 inches, which is 1/3 of a foot. I use the formula F equals Kx. The force is equal to K times X. That's sometimes called Hooke's law. And you can solve for K. So plug in 10 right here. Plug in 1/3 here. 10 equals K times 1/3. Multiply both sides by 3. So K is equal to 30. So F equals Kx is now F equals 30x. Put a 30 there. So that's my force function. F equals 30x. And now that's basically what I'm going to integrate. Okay, so you integrate the force function, just like the problem from last time. Right? You had a variable force. So that's what you integrated. You integrated the force function. Okay, so it said you're going from 0 to 6 inches, which means 0 to half a foot. So my integral is from 0 to 1/2 of the force function, 30x dx. Okay, so that's pretty easy. So 30x squared over 2, from 0 to 1/2. 30 over 2 is 15. So plug in 1/2, 1/2 squared. Plug in 0, you get 0. That's very nice. Final answer is 15 over 4 foot-pounds. Okay, so that's a unit of work. So in the English system, the unit of work is the foot-pound. Remember, in the metric system, it was joules. Okay, and I gave you all of that last time. And again, if you're not comfortable with all that stuff, put it on your cheat sheet. You're allowed to do that. All right, so that's that one. Okay, another one I want to show you would be 15, please. In case you're, saying to yourself, boy, it sure looks like he's doing a lot of the problems. You're right. I'm doing a bunch of the problems. Sometimes I end up doing almost all of them, or literally all of them. And then you just have to go back and review them for yourself. Okay, a cable that weighs 2 pounds per foot is used to lift 800 pounds of coal up a mine shaft 500 feet deep. Find the work done. Okay, so you have a cable that's 2 pounds per foot, 800 pounds of coal, 500 feet deep. Find the work. Okay, so again, is that metric or English? I see pounds and feet, so it's English. All right, so I've got a picture of the situation here. All right, so here's the cable. You got 800 pounds of coal at the bottom. Okay, the cable itself weighs 2 pounds per foot. You're bringing all of this coal up, but you're also bringing up the cable. Okay, so how much work is there in bringing the coal up and also the cable? Okay, so here's x equals 0. Here's x equals 500. Okay, I'm going to split this into two parts, two problems. Okay, there's a certain amount of work for the coal, 800 pounds, and then there's a certain amount of work for the cable. Okay, so I put W, work for coal, C-O-A-L, and work for the cable. Okay, so I have to bring the cable up, and I have to bring the coal up. Now, for the cable, it's not going to be the same amount of work, because after all, if a piece of cable is very close to the top, right, it doesn't have to go that far, but something way down here has to go farther. Okay, I mean, I don't know if this brings the point home. Pretend this is people, okay? You want all the people to come out of this mine shaft. Well, if you're already up here, you don't have to go that far. But if you're way down here, you've got a lot more work to do to get to the top. Is that right? And you have all this coal. Okay, now, Remember I mentioned last time the gorilla problem? For the coal part, it's just a gorilla problem. See if I can show you again the gorilla problem, which was just simply work equals force times distance. 300-pound gorilla times 20 feet, right? Nothing variable about it. This is the gorilla problem. All the coal is 500 feet underground, and you're bringing it all 800 pounds up. So that's just like the gorilla problem. The work for the coal, C-O-A-L, if you can't read that, is just 800 pounds. They're all going up 500 feet. So 800 times 500 comes out to be 400,000 foot-pounds. So the work for bringing the coal up is 400,000 foot-pounds. That's the easy part. So now I have to figure out the work for the cable. Okay, that's a little bit harder because it's not going to be constant, right? Now I chop into this tiny piece here. Remember, there's other pieces. There's a piece at the top and here and all the way down, right? Chop, 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 chop in a whole bunch of pieces. Let delta x approach 0. Let n approach infinity. We end up with the integral, right? Okay, so for this particular slice, if delta x is really, really small, it is the gorilla problem. Now, you might argue, well, the distance traveled by a piece at the top is a little bit smaller than the distance traveled by the piece in the bottom. And you're right. Okay? But again, if delta x is really, really, really small, okay, from the approximation, we can just assume in the limit that it's constant. Okay? So I have to take the force, which really means weight, times the distance. Okay? Well, the distance is x. So if I'm literally at the top, I travel nothing. If I'm at the bottom, I have to travel 500 feet. If I'm somewhere right in the middle, that's 250 feet. Here it's 200 feet. Here it's 100 feet. Here it's 400 feet, and so on, right? So in general, it's x feet. Okay, now I have to translate this into a weight. So how much does this tiny little slice of cable weigh? Well, the units would be pounds, right? I know it's 2 pounds per foot. Okay. So my delta W, the change in work, it's 2 pounds per foot times delta x feet. Okay. And if you look at the units analysis, right, that foot will cancel that foot. So you have 2 delta x pounds. So the weight of that slice is 2 delta x. Okay. Again, you can just think of units analysis. Okay, 2 pounds per foot, and you say, okay, I want to cancel the feet. Well, how many feet do I have? Delta x. Okay, so this is the force. 2 delta x pounds, feet cancel out. How far does this piece of cable have to travel? X feet to get to the top. X is a variable. If I'm way up here, you travel 0. If you're here, it's 100, 200, 300, 400, 500, and all the other numbers in between. So I multiply that by x feet. So if you look at the units right now, the units are pounds times foot or foot pounds. And that's what I want. 2x delta x foot pounds. And that's what I got. Okay, now I'm ready to integrate. So the work for the cable, I just integrate. In the limit, delta x becomes dx. So I integrate from where to where? I'm going from 0 to 500, right? 0 to 500. Integral from 0 to 500 of 2x. Delta x becomes dx. And now the rest is pretty easy. Integral of 2x is x squared from 0 to 500. Plug in 0, you get 0. Plug in 500. 500 squared is 250,000 foot-pounds. All right, so for me to bring up the cable is 250,000 foot-pounds. To bring up the coal was, where would it go? 400,000 foot-pounds. So for the total work, I just add them together. So the grand total is 400,000. That's for the coal. That was constant. That was easy. That was just a gorilla problem. Plus 250,000 for the cable. Grand total is 650,000 foot-pounds. Okay, so that's that one. 13, I wasn't going to do. I mean, if I do it, I'd end up almost doing them all. but I would just say it's similar to 15, except there's no coal. Let's see what that's talking about. So look quickly at 13. Where is 13? And by the way, it's 13A, just 13A. I'm not sure if I said it. Skip 13B, please. Oh yeah, I got it here. 13A. All right, we're good. Okay, a heavy rope, 50 feet long, 0.5 pounds per foot, hangs over the edge of a building, 120 feet high. How much work is then in pulling the rope to the top of the building? Okay, so work it out just like 15, except there's no coal. You have this rope hanging over the edge, 50 feet, and there's the density. So it's just different numbers. Let's see. You don't really use the 120 feet. It's irrelevant. Okay? If the rope is hanging over 50 feet, well, as long as the building is at least 50 feet. If the building is 40 feet, then it wouldn't work, right? But if the building is 50 feet or more, then you can use it. So don't use the 120 in the problem at all. Use the 50, use the 0.5, and then it's pretty much just like the one I just did, right? It's a different density there and a different weight, but otherwise work it out the same way. Okay. Okay, last one, 23. It's a little bit harder though. This one's metric. So let me see if I can get that for you. A tank is full of water. Find the work required to pump the water out of the spout. Use exercise 24. Okay, we're not using that. Okay, so here's the picture. Okay, this weird looking tank, I guess I sometimes call it a trough, T-R-O-U-G-H. Okay, it's full of water. So it's 3 meters here, 3 meters across, 8 meters this way, and you're pumping the water all out of the spout here. Okay. Now, it's 8 feet this way uniformly. Okay, now, I can't draw, so all I'm going to show you, so I can show you it's pretty much equivalent. I've got this. It's only the front. I can't draw, but I know it's 8 meters deep. Okay, so this triangle here is this triangle, and there's the top of the spout. That's as much as I want to draw, and it goes 8 meters deep. Okay, so I'm going to analyze this picture. There's 2 meters here, 3 meters here, 3 meters across there, and I'm not drawing it, but it's 8 meters deep. Okay, so I'm going to lose the book now. Okay, so how can I figure this out? So here's my cross-sectional slice. So this is kind of like the aquarium problem. Remember we did the aquarium problem? Okay, I will slice like this. Now you might say, how do you know to slice this way and how come I don't slice this way? Because if I slice this way, all the water molecules are traveling the same distance up the spout. Okay, so if I slice it like that, right, then all the water molecules are not traveling the same amount. But all the water molecules here are traveling the same amount. Okay, I'm going to call this x equals 0. I'm going to call this x equals 3. Now you might be saying, well, how come the other time you put 0 here and you put, the bigger number here? There's a reason for that. I'm taking advantage of similar triangles here from the picture. Okay, now by similar triangles, the ratio of the height to this length is equal to the height to the length here, but they're equal from similar triangles. Okay, one more time. If this altitude is 3 and this is 3, that means they're equal. So for this smaller triangle, by similar triangles, then the ratio of this height to this length also is equal. So if this is x, this is also x. That's going to help me in this picture. Okay. So at the bottom, x is 0. At the top, x is 3. Maybe here x is 1. In general, I have x. And by similar triangles, this distance is x. Now, mind you, this thing is going back 8 meters, right? I can't draw it. It's going 8 meters back. So I have to figure out the weight of that sandwich of water. Okay, remember, that's going back 8 meters. Okay, so first I need the volume of that slice. The volume is x by a tiny delta x by 8. It's 8 meters back. So here's the volume. X meters by delta x meters by 8 meters. So at this stage of the game, I have cubic meters, right? Length times width times height. Can you say, hey, it's not a rectangle? You're right. But if delta x is really, 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 really small, it looks more and more like a rectangle. It's more rectangular-ish. And in the limit, it is a rectangle. Okay, so it's x by delta x by 8. Okay, so right now I have meters cubed. Okay, so we're playing this game of units analysis again. We got this from units analysis. So right now I have meters cubed. I can convert it to kilograms because I know water is 1,000 kilograms per meters cubed. You can put that on your cheat sheet if you want. Okay, so the density of water is 1,000 kilograms per meters cubed. Now meters cubed cancels meters cubed. See how I've lightly marked off that meter, 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 and meter cubed? They're all gone. So at this stage of the game, I have kilograms. You just kind of get the units to line up the right way. So meter, 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 meter cubed cancels that meter cubed. So now I have kilograms. Okay, and then I multiply by the acceleration due to gravity on Earth. Okay, that's 9.8 meters per second squared. Okay, we're making the assumption all of our work is on Earth, obviously. Okay, so this is called the acceleration due to gravity. The abbreviation is G. Okay, acceleration due to gravity, and you physics people know this. Acceleration due to gravity on Earth. And there's a different acceleration due to gravity on the moon or Mars. Okay, but on Earth it's 9.8 meters per second squared. Okay, so right now at this stage of the game, I have kilogram meters per second squared. Kilogram meters per second squared is newtons. So this is all newtons. Now to convert it to work, I multiply it by the distance. Work equals force times distance. So how far are these water molecules traveling way up to the top? Okay. So the way we figure it is the distance from the bottom to the top is 5. Right? Because they said this was 3, this is 2. So this is 5. And we declared this to be x. This distance here is x. So if from here to here is 5, here to here is x, the distance that these water molecules have to travel is 5 minus x. That game again. Okay, so again, this is 5 from here to here. This is x, so this is 5 minus x. That's the distance that all the water molecules are traveling. So now I multiply by 5 minus x meters. So at this stage of the game, I have Newton meters, and Newton meters is joules. Okay, so that's the hardest part, is just setting it up. The actual integral is not that bad. So that's it. Okay, so one more time. First, I had to find the volume of that slice. Remember, it goes 8 meters deep. So it's length times width times height. Length is x. Tiny little height is delta x. And the width was 8. So right here, I have meters cubed. If I multiply by 1,000 kilograms per meters cubed, this meters cubed cancels this meters cubed. So now I have kilograms. Change it to a force. Multiply by 9.8 meters per second squared, acceleration due to gravity on Earth. So I have kilogram meters per second squared. Kilogram meters per second squared is Newton. That's a unit of force. That's the weight. That's the weight of that sandwich of water. How far do those water molecules all travel? 5 minus x. Okay, so what did I do here? I multiplied 8 times 1,000 times 9.8. That comes out to be 78,400. And let's see, I have an x times a 5 minus x times a delta x. So if we count for everything, number times that number times that number comes out to be that. There's x, there's 5 minus x, and there's delta x. And that's the number of joules. And there we go. So all that's left now is to integrate that. In the integral, delta x becomes dx. So you integrate 78,400x 5 minus x. And the integral is from 0 to 3, not from 0 to 5, because there's only water from 0 to 3. Okay? Originally, there's no water up here, so you integrate only from 0 to 3. And I just say etc. You can do the rest of that pretty easily, I think. Okay? Factor out the 78,400. That's 5x minus x squared. That's pretty easy. You take it from there. Okay? All right, so I'm actually done with 6.4. I'm going to get started with 6.5, and I'm actually going to try to finish everything I need to for 6.5 before the day's over. It's not that long. In my opinion, it's the easiest section. Okay, I mean, yeah, 6.1, 6.2, 6.3, 6.4. If you know this, you'll be relieved at 6.5. Okay, I think all of you should be relieved at 6.5. It's pretty easy, in my opinion. Of course, I know my opinion doesn't really count sometimes, but 6.5. Okay, it's on the average value of a function. So 6.5, average value of a function. Here's the formula again. You can put it on your cheat sheet. F average, AVG. Well, it says AVE. I like AVG. 1 over b minus a, integral from a to b of f of x dx. Okay, 1 over b minus a is basically the length of the interval. Okay, and I'll give you a little bit of theoretical background as to what's going on for the average value of a function. Okay, so a little bit of theory. Okay, I have a function that goes like this. Here's my f of x going from a to b. I picked a positive function because I like it, but it doesn't have to be a positive function. Okay, what would I consider to be the average value? Well, we decided this. I know how to find the area under this curve, right? Integrate. I know how to find the area of that rectangle, base times height. We will define the average value to be that height so that the area of this rectangle matches the area under the curve. See that? I want the area under the curve and the area of this rectangle to be the same. So if a graph goes like that, you know you're not going to pick the smallest value, right? If I take the smallest value, you can tell that the area of this rectangle is clearly much smaller than the area under the curve. And you don't want to pick the biggest one either. If I pick the biggest one, that looks like the area. That's clearly too big, right? So you want something, quote unquote, in between. Okay. So that means I want F average. Again, my average is AVG, not AVE. Okay. To me, AVE means avenue. But anyway. So I want the area under the curve, integral from a to b of f of x dx, to equal the area of this rectangle. So how do you find the area of that rectangle? It's base times height. The height is f average. And how far is it from here to here? It's just b minus a. Right? Like if this is 3 and this is 10, you would just go 10 minus 3, right? So it's f average times b minus a. If you divide both sides by b minus a, or multiply by 1 over b minus a, you have the formula. So there we go. F average is 1 over b minus a times the integral from a to b of f of x dx. Okay, and if you want to think of what's really going on, you're taking the area divided by the length. Okay, so imagine taking the area under the curve and dividing by the length of the interval, then you have the average height. Okay, another way of thinking of it is you can take all this area. Okay, I'm tracing it out, right? You go like that, and like that, and like that, and like that, right? You can rearrange that same area so that it ends up looking like that. If you chop some of this and kind of put it there, it looks like that. Okay, essentially, it's just area divided by length, but normally we're just going to go 1 divided by length and then the integral. Okay, and that calculation really is not that bad, folks. Okay, I mean, you all know how to integrate. Just remember, to me, the easiest thing for students to forget is this part. Make sure you go 1 over the length of the interval. Okay. So that's basically it. So let me just do a bunch. And there we go. Okay, so number one, what time is it? It's almost 8 o'clock. Okay, so the function is 3x squared plus 8x going from -1 to 2. You don't have to draw a picture. No picture necessary. So all you do is you integrate from -1 to 2, but you have to multiply by 1 over b minus a. 2 minus a minus 1 is 3. In other words, the length of this interval is 3, right? From -1 to 2 is 3 units. You're just going to take this integral and divide by 3, or multiply by 1/3. So it's going to be 1/3 integral of 3x squared plus 8x dx. That's all. So what's the integral of 3x squared? 3x cubed over 3. 3x cubed over 3 is the same as x cubed. What's the integral of 8x? 8x squared over 2. That's the same as 4x squared. And by the way, how can you ever check an integral? Take the derivative, right? Very common technique, right? You say, I wonder if I integrate it right. Take the derivative. What's the derivative of x cubed? 3x squared. What's the derivative of 4x squared? 8x. So it works. Okay, leave out the 1/3. Okay, paren, plug in 2, minus paren, plug in -1. So put a 2 here. 2 cubed is 8. Put a 2 there. Let's see, 2 squared is 4. 4 times 4 is 16. Minus parentheses, plug in -1 there, and -1 there. -1 cubed is -1. -1 squared is 1. 1 times 4 is 4. Okay, so that's what? 24 minus 3. So 1/3 of 24 minus 3, that's 1/3 of 21. Final answer is 7. Okay, so the average value of this function on the interval from -1 to 2 is 7. Notice it is dependent on the interval. If I choose a different interval, then the average value might be different. Like if you say, what's the average value going from 10 to 25? Well, obviously, it's not necessarily going to be the same as what I have over here. In fact, I know in this case, it isn't going to be the same. Okay, so that's the basic idea, folks. So I think you would agree this is much easier. Just integrate, multiply by 1 over b minus a. You're dividing by the length of the interval. Okay. Next one I'm going to show you is number 5, and I apologize. I've got this line through it like I was crossing it out, but I crossed off too much. Okay, so ignore this cross out here. Sorry. We're doing number 5. Okay, f of t equals e to the sine t cosine t from 0 to pi over 2. You don't have to graph it. Actually, this is a very difficult graph. E to the sine t times cosine t. Okay, sorry about that line there, but we're doing it. Okay, so by formula, I go 1 over b minus a, 1 over b minus a times the integral. So what's b minus a? Whoops. It's pi over 2 minus nothing, which is pi over 2. So 1 over pi over 2 minus nothing. And by the way, what's 1 over pi over 2? That's like saying the reciprocal of pi over 2 is going to be 2 over pi eventually, right? 1 over pi over 2, 2 over pi. Then I integrate from 0 to pi over 2, e to the sine t times cosine t dt. All right, here's a perfect example of a u substitution that you had at the end of Calc 1. Okay, so you say, how do you know to substitute? Okay, I would make the problem a lot easier if instead of having e to the sine of t, I just have e to the u. Okay. And furthermore, I see the derivative of sine t elsewhere in the problem. What's the derivative of sine t? Cosine t. Right? So that tells me how to substitute. Okay, on two fronts. I can make it easier if I said e to the u, and then I also ask myself, do I see the derivative of sine of t elsewhere in the problem? Yes, cosine t. So that's how I substitute. So that u equals sine of t, du equals cosine t dt. That's the way we write it. If that bothers you, remember using the so-called Leibniz notation. This is sometimes called the Leibniz notation. L-E-I-B-N-I-Z. You don't have to know that. But remember in Calc 1, you had the D stuff, right? dy dx or du dt. That's called the Leibniz notation. So you probably went from here to here in Calc 1, didn't you? If u equals sine t, one of the symbols for derivative would have been du dt equals cosine t, right? The d notation, that was sometimes called the Leibniz notation. I'm not testing you on the Leibniz notation, but I'm just telling you. Okay, from here, if you multiply both sides by dt, it looks like this, right? If you go times dt, that's gone. If you put times dt there, it looks like this. But usually we're just going to go straight to here, and that's what I want you to do. So this side that has a u, right? Just put du, and then sine t, cosine t dt. And now I substitute. So I got these circled here. The next step, I will replace sine t with u, because u equals sine t. So instead of e to the sine of t, I'll have e to the u. And instead of cosine t dt, I'll just have du. And then one extra thing, we have to change the limits also. The 0 and the pi over 2 are for which variable? They're for t. I'm going to change the problem so that it's all within u. So I have to ask myself, as t goes from 0 to pi over 2, what happens to u? U goes from something to something, right? So what do? I plug in, okay? So t equals 0. Put a 0 here. I got sine of 0. Sine of 0 is 0. So when t is 0, u equals 0. And then I plug in the upper limit, pi over 2. Sine of pi over 2, sine of pi over 2, 90 degrees, that's 1. Okay? So in other words, as t travels from 0 to pi over 2, u travels from 0 to 1. So my new integral is going to be completely in u. I'm going to forget about t. I'm not going to have this t. I'm not going to have this t or dt. And these numbers are for t. I'm going to switch it to u, du, and even these limits are going to be u. So I'm totally forgetting the old variable of t. I'm burning that bridge, so to speak. I'm just going to integrate with respect to u. So I'm no longer integrating from 0 to pi over 2. I'm now integrating from 0 to 1. Okay, so 0 to 1. E to the sine of t becomes e to the u. And cosine t dt is du. And there we go. And now it's hopefully fairly straightforward. So the integral of e to the u is e to the u from 0 to 1. The reciprocal of pi over 2 is 2 over pi. So I have 2 over pi. You can factor it out. Plug in 1. You have e to the 1. Well, e to the 1 is just e. And minus plug in 0. You have e to the 0. Well, e to the 0 is 1. So 2 over pi times e minus 1. Okay. All right, ignore that. Okay, next one I'm going to show you is number 9. What time is it? Almost 8:05. Okay, so bear with me, please. I want to make sure I get at least one session in case we're gone for the rest of today. I want to get that in, so sorry about that. Okay, 9. F of x equals parentheses x minus 3 squared from 2 to 5. And this one, they actually give us a little bit more stuff. So here's 9 and 11. Find the average value. We know how to do that. Find C such that F average equals F of C. Okay, that leads us to something called the mean value theorem. I'll show you that in a second. And sketch the graph of F and a rectangle whose area is the same as the area under the graph of F. Well, that sort of goes along with what I talked about. Okay, let me show you the mean value theorem for integrals. Okay, so this is on page 462. You might remember there's a mean value theorem in Calc 1. That was for derivatives. Mean value theorem for integrals. If f is continuous on the closed interval from a to b, there exists a number c between a and b such that f of c is the average value. Here's the formula for the average value, 1 over b minus a, integral from a to b of f of x dx. Okay, so what does all that mean? So here's a picture, sort of like what I had. Okay. I was showing you, right? Here's f average. Here's a similar picture. They're showing you this is the average value. So if you take the area under this curve, okay, I'll trace it again, that up, curve down, that has a certain area. It's the same as the area of that rectangle. Okay. Now, what does the mean value theorem say? If I draw this picture, if you have a continuous function, like this is, okay, then the average value hits the graph. As you can see, it hits right here. That x-coordinate is called C. That's what they mean by C. That's what all that language means. Okay? If you have a continuous function, the average value touches the graph, as you can see there. For the picture that I have here, for the average value, here it is. Okay, so for this picture, this would be what they call C. It doesn't have to be exactly in the middle. By the way, you could have more than one C, but there has to be at least one C. That's what they're talking about there. It has to touch. As long as it's continuous. If you don't have a continuous function, then you can see if I break it, right? If I have a picture and then I jump over to there, then sure, the average value might not touch the graph. But for continuous functions, the average value has to touch the graph, like here and like here. Okay, so how do I apply that now for this problem? F of x equals x minus 3 squared from 2 to 5. Okay, we know this is just x squared translated 3 units to the right. Okay, remember our rules for translation, moving it 3 units? So x squared was like that, right? X minus 3 squared, I moved the graph 3 units to the right, so it looks kind of like that. And we're only going from 2 to 5, so that's all I drew. And I plugged in some numbers. What do you get when you plug in 2? 2 minus 3 is negative 1. Negative 1 squared is 1. Plug in 3, you get 0. Plug in 4, you get 1. Plug in 5. 5 minus 3 is 2. 2 squared is 4. So it looks like that. So there's an average value somewhere. Okay, so just plug it into the formula. So I go 1 over b minus a. What's b minus a? 5 minus 2, which is 3. Which happens to be the length of the interval. That's how far it is from 2 to 5. Right? So the length of the interval is 3, so I have 1/3. Then I just integrate. Integral from 2 to 5 of x minus 3 squared dx. Okay. If you're wondering, in this particular case, you can just use the power rule. You don't have to multiply this out. That'd be harder, right? Like x squared minus 6x plus 9. You can just integrate like that. And this might go a little bit deeper than I want to go now. It's because the derivative of the inside happens to be what? What's the derivative of the inside? It's 1. Okay, that's what allows me to just go straight to the power rule. Now, if this was x squared minus 3, I couldn't do that same trick. Okay, the chain rule in reverse wouldn't work. You'd actually have to multiply it out. But as it stands, 1/3 x minus 3 cubed over 3. Okay? And again, you can double check that. Ignore the 1/3 right now. What's the derivative of this thing? Right? If you differentiate this, 3 comes down, cancels that 3, right? So you would have x minus 3 squared, then by the chain rule, times the derivative of the inside. But the derivative of the inside is 1, so it works. I have x minus 3 squared. But that would not work, let's say if that had been x squared, then by the chain rule, you know, when you take the derivative of the inside, you got to have an extra 2x, so that opens a different can of worms. So we wouldn't be able to do that. Okay, so anyway, let's see, 3 times 3 is 9, so I make that 1/9. Okay, so I'm combining this in 1/9. So I'm just looking at this. So I plug in 5. 5 minus 3 is 2. 2 cubed is 8. Minus, plug in 2. 2 minus 3 is negative 1. Negative 1 cubed is negative 1. So I have 8 minus a minus 1. 8 plus 1 is 9. So I have 1/9 of 9, which is 1. So the average value is 1. And there it is. So I've drawn it for you. Okay. And does it touch the curve? Yes, looks like in 2 places. So again, conceptually, the area under the curve of that parabola matches the area of that rectangle. Okay, now they want you to find the C's. That means where do they touch? Well, you can just look at the picture. It touches at 2 and at 4. Okay, but how would you prove that? Okay, so I just take the function x minus 3 squared, right? And I just set it equal to 1. So x minus 3 squared equals 1. Take the square root of both sides, put a plus or minus. X minus 3 equals plus or minus 1. And add 3. So x is 3 plus or minus 1. 3 minus 1 is 2. 3 plus 1 is 4. So the C values, plural, would be 2 and 4. You're allowed to have more than one such value of C, but the mean value theorem says there has to be at least one such value. Okay? Well, the picture that I drew over here, there was only one, right? Right here somewhere. And the example that they gave in the book, here, there was only one. But they give you another picture like this, where it looks like it touches in two places, -1 and 1. So you could touch it in a whole bunch of places, but the mean value theorem says it has to touch at least once. Okay. So that's problem number 9. Okay, so go a little bit more. Let's see that. F is continuous, and the integral from 1 to 3 of f of x dx is 8, so that f takes on the value 4 at least once on the interval from 1 to 3. Okay, that's really just using the mean value theorem. Okay, so let me show you what that's about. Let me get a separate piece of paper for that. So for 13, integral from 1 to 3 of f of x equals 8. From 1 to 3. Okay, show that it takes on the value of 4. There's really not that much to it. So F average by formula is 1 over b minus a, integral from 1 to 3 of f of x dx. That's 1/2. They told us that this is 8. And I get 4. And they told us that f is continuous. So there it is. Okay, so by the mean value theorem, there exists a C between 1 and 3 such that f of C is equal to 4. That's pretty much just using the mean value theorem there. Okay, hang in there a little longer. I know it's late, but I want to get this in case we never make it back again. A little bit longer. Okay, I want to show you 15, please. Find the average value from 0 to 8. Okay, the length of the interval is 8, right? I need to find the integral. Okay, so to find the integral, I'm really just counting squares here, as it were. So I'll do a running tally, as it were. So 0 to 1. So let me go like this. So for problem 15, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. Okay, maybe I'll go like that. No, I'll just make it into a table. Sorry. Okay, 0 and 1. It's below the x-axis. So you might recall from Calc 1, if it's below the x-axis, it's going to be a negative, and that looks like half a unit. So negative 0.5 because this is below the x-axis. Then from 1 to 2, that looks like half a unit above the x-axis. In fact, all the rest are above. So this is a positive 0.5. So right now they cancel out, the answer would be 0, right? So again, this piece bounded by the graph and the x-axis is below the x-axis. So we want the opposite of the area. So it's negative 0.5. This one is a positive 0.5. 2 to 3 looks like another 0.5. See what I'm doing? I'm basically counting squares. 3 to 4, well, it's a triangle. 1/2 base times height. So it's 1/2 of 1 times 2, which is 1. Okay, so the area under the curve graph from 3 to 4 is 1. Or here's another way you can think about it. This is clearly 2, right? That's 1 square and that's 1 square. And that line there cuts it in half. So that's going to be 1. Okay, 4 and 5, 1, 2. Between 5 and 6, 1, 2. Right? There's 2 squares there, 2 squares there. Between 6 and 7, it's 1 and a half. 1.5. And then between 7 and 8, I have 1 plus 1. 2. This piece right here is, again, 1 unit. Again, if you take this thing, that's clearly 2 squares, right? That's 2 squares. That cuts it in half. So that triangular region is 1, and that's another 1. So that gives me 2. So one more time, net area under the curve as an integral. From 0 to 1, it's negative 0.5. That's a positive 0.5. Another 0.5. That looks like 1. Between 4 and 5 is 2. Between 5 and 6 is 2. 6 and 7, that's 1 plus a half, 1.5. And that looks like 2. Okay, so I just add them all up. These two cancel out. So let's see. Let me get rid of the decimals. So ignore these two. These two combine to be 2, right? So 2, 4, 6, 8, 9. Grand total is 9. Ignore these, they cancel out. I did 0.5 times 1.5 is 2, 2, 4, 6, 8, 9. Okay, so that means the integral from 0 to, what was it, 8? Is 9. So therefore the average value is 9 over 8. So my answer is just 9 over 8. Okay, I think I will stop there. It's 8:20. Okay, so here's what's going to happen now, folks. Don't leave yet. I will stop the share, and let me see. Oh, what do you know? It looks like I can pause the recording, so sorry you don't get to go home, as it turns out. Okay, I'll hit pause. So I'm recording now. Okay, back to record. Share the screen. And here we go. I think. Get it right. There we go. All right, so one more time. I'm ahead, okay, because I had 6.5 on Thursday, but I think I'm finishing it today. I might even sneak in a little bit of 7.1. Okay, now even though I'm a little bit ahead, I'm not going to stop. Okay, something might happen. I might get sick, or I can't keep up as fast, so I'll just keep going. But so I'm finished with everything by today of 6.5, but I'm not changing the test date. Test is here. So first half, I'll do more stuff. Maybe I'll even get to 7.2 by then, who knows. But the second half will be the test. You say, what do I turn in? Only this. And I've already done a whole bunch of them anyway, right? It's okay if it's out of order, because you know how I jumped around, right? I did like 1, 5, 13, and you have to reorder them. It's only if you want to. You don't have to. And so I'll start a little bit of 7.1 today, but that won't be in the test. your coverage is here. So if I give 10 questions, right, then that looks like maybe two per section, right? I'll give you two of these, two of these, two of these, two of these, and two of these. Are they going to be the very same question? Probably not, although I'm allowed to give you the very same question, but I might just modify it a little bit. Okay. All right, so the only one I wanted to show you extra was 17. I mean, 6.5, so you finished it all in one day. Well, yeah, it's a fairly easy section, I think. I think you would agree. This is the easiest of the sections. Okay, so the last one I was going to show you was 17. So they say T of T. Now, what's this T of T stuff? Okay, capital T is for temperature, little t is for time. So that's often used. Capital T of little t, T of T, temperature, time. Here's a formula, 50 plus 14 sine of pi t over 12, okay, over a 12-hour period. And they say find the average value over a 12-hour period, which means it's 1 over 12, integral from 0 to 12 of 15 plus 14 sine of pi over 12t dt. Okay, so they just want the average value of this function over a 12-hour interval. So 0 to 12. Okay, now this is pretty easy, 50t. I'm going to take a little time out. So a little time out. Let me work on sine of pi over 12t. So this box here is a little timeout. Okay, trying to show you something in reverse. Now you could do some of these integrals by use substitution, like that one you could, and that one you could, but I don't think you have to. I'm going to try to argue from the chain rule in reverse. So think back to Calc 1. What was the derivative of e to the 2x with respect to x? So you saw this notation, hopefully, d dx, e to the 2x. You went e to the 2x. Then by the chain rule, it's times the derivative of the exponent, which is 2. So the derivative is 2e to the 2x. You had to multiply by 2. That was the chain rule. Please make sure you understand the chain rule, because if you don't understand the chain rule here, you're not going to get it here either. Okay, so remember the chain rule? To differentiate e to the x, it was e to the x. What if I had e to a function of x? Then you put down e to that function, and then times the derivative of the exponent. So the derivative of e to the 2x is e to the 2x times 2. Okay? All right, so to differentiate, I multiplied by 2. So guess what happens when I integrate? I don't multiply by 2, I divide by 2, or multiply by half. Since integration and differentiation are opposite operations, okay, if I look at this, right, and say integral of e to the 2x, e to the 2x times 2. So integrate e to the 2x divided by 2, or multiply by 1/2. And then technically plus c. Remember, this is an indefinite integral. Indefinite integrals, I have to put the plus c. And again, how do you check an integration? Differentiate. What's the derivative of this thing? Well, of course, the derivative of any constant is 0. The derivative of 1/2 e to the 2x is 1/2 e to the 2x times 2. Well, if you multiply by 2, that knocks out that 1/2, and you get this back. Perfect. Okay, let's try this. What is the derivative of sine 3x? I wrote it like this, sine of 3x prime. That's a prime, like the derivative. So derivative of sine of 3x is cosine 3x. And then by the chain rule, times the derivative of 3x, which is 3. Right? Remember that from the chain rule? Please make sure you recall that. Again, if you don't understand the chain rule there, you're not going to understand it here. So derivative of sine 3x, cosine 3x times 3. Okay. Key concept, I multiplied by 3. So guess what happens if I integrate sine of 3x? Over here, you multiply by 3. You divide by 3, or multiply by 1/3. Okay, so the integral of the sine is negative the cosine, you might recall. So negative cosine 3x times 1/3. So here we go. Okay, remember, the integral of sine is negative cosine, not the derivative. The integral of sine is negative cosine because the derivative of negative cosine is sine. Again, double check by differentiating. What's the derivative of negative 1/3 cosine 3x. The derivative would be positive sine, right? Derivative of cosine is negative sine. So the derivative of negative cosine is sine. So you would go sine 3x, then by the chain root times 3. Well, that 3 knocks out that 1/3, so it's perfect. Okay, that's the end of the timeout. So I call it time in now. The game is beginning again. So when I get to this stage, if I want to integrate sine pi over 12t, okay, if I differentiate sine pi over 12t, I would multiply by an extra pi over 12, chain rule. So when I integrate, I multiply by the reciprocal, 12 over pi. So it's going to be 12 over pi. Okay, so finally, here we go. Integrating this. Integral of 50, 50t. 14 is a constant. Okay, integral of sine is negative cosine. So negative cosine pi over 12t. And then by the chain root times 12 over pi, just like all these other ones that you multiply by the reciprocal. Right? So again, if you differentiate sine pi over 12t, you get cosine pi over 12t times pi over 12 by the chain root. If you differentiate. So if I differentiate, I multiply by pi over 12. Therefore, if I integrate, I multiply by 12 over pi. And there it is. So 50t, whoops, where am I? 50t, right here. There's the 14. Integral of sine is negative, so negative cosine pi over 12t times 12 over pi. And I'm integrating from 0 to 12. Okay, this looks a little bit complicated, but I plugged in 12 here, 50 times 12. Put a 12 here. I've got 12 over 12, which is 1, pi. So negative cosine pi. Minus, plug in 0. Put a 0 here, you get 0. But not over here. Put a 0 here. 14 times 12 over pi. Put a 0. You've got negative cosine of 0. Put a 0 right there. Negative cosine of 0 is negative 1. Now look at this little trick that I did. Cancel that 12 with that 12, that 12, and that 12. That way I never have to pick up my calculator and figure it out. That 1/12 distributes, cancels that, that, and that. So very conveniently, I have 50 plus 14, okay, negative the cosine of pi. Cosine of pi is negative 1. So the negative of that would be positive 1. So that's 1. So that's 14 over pi minus negative 14 over pi. So minus negative 14 over pi is another plus 14 over pi. So 50 plus 14 over pi plus another 14 over pi. Final answer is 50 over 28 over pi, which is approximately 59 degrees. And by the way, here's an example where the appropriate answer is to give it as 59 degrees because it asks for the average temperature. I mean, it's just, how do we normally say temperature? Nobody talks like this, right? So if I say, oh, what's the temperature? Am I going to say, oh, the temperature right now is 50 plus 28 over pi? Nobody talks like that. So we would round it off here to 59 degrees. So here, even though it doesn't say so, it's appropriate to give the answer as 59 degrees. Okay. All right, that is 17. And now, folks, I am indeed actually finished with the chapter. So I'm a little bit ahead. So coverage for the test is everything up to now. Okay, 6.1, 6.5. I'm going to start some of 7.1, very little. Whatever I do now won't be on next Tuesday's test. It'll be on the next test, okay, which right now is tentatively what? Looks like October the 1st, I guess. Okay. Yeah, I might change this. We'll see how it goes. But as of now, I'm a little bit ahead, but who knows? I might fall behind. I might fall back. I might get sick, or, you know, who knows? So I'll just keep going in the meantime. So I will introduce 7.1. I'm just basically going to give you the formula for it, do one problem, and then stop. Okay, so let's see. It's 8:45 now. I'll probably be done around 9-ish, and then I'll let you ask questions. Okay, so introducing 7.1. Take notes, but don't study it for next Tuesday's test. Okay, but go ahead and take the notes. Okay, chapter 7 is more techniques of integration. Techniques of integration. This chapter is integration, integration, and more integration. Okay, lots and lots of integration. First type is something called integration by parts. Integration by parts, 472. Here's the formula. You can put it on your cheat sheet. Although if we were meeting face to face, I'd make you memorize it. But since we're not making you memorize it because of COVID and all that stuff, they told us to, relax some of the restrictions. That's what I'm doing. Integral of u dv equals uv minus the integral of v du. Yes, I agree. If you've never seen this before, you say, huh? What are you talking about? Okay, so don't worry about that right now. Go ahead and get the formula down. Integral of u dv equals uv minus the integral of v du. Okay. And while I'm at it, I might as well start showing you some of 7.1. Okay, for those of you who never want to get the book. Okay, so 476, 7.1. Yeah, I can fit it there. Notice it's all integration problems. Everything here is integration, right? So maybe that's the best I can do. The evens don't come out so good, but I don't think you have to do any evens anyway. So that, okay, then the next page, what is it, 477, I guess, up here. So there's the top of it. So I got down to maybe 55. Okay, whoops. A little bit more. And more. Maybe go back a little just in case. Okay. And we don't have any on the next page. Okay, so I think we're good there. All right, so integration by parts. 7.1, integration by parts. Ignore the date, of course. Okay. If we had met face-to-face, I would show you the derivation. Since we're not meeting face-to-face, I'm just showing it to you. How do I come up with this formula? Here it is. So I'll just show it to you. You can look at it or not. Okay. It basically comes from the product rule. Right? How do you take the derivative of a product? U of x, v of x. Okay. It's the first times the derivative of the second plus the second times the derivative of the first. Right? I'm not testing you on this. So frankly, if you want to just tune out for a moment, you can. Okay. But I'm just showing you quickly. Okay. So derivative of u of x, v of x is that. If I take off the x there, take off the x, you can shorten it to the derivative of uv is u dv dx plus v du dx. If I use differential notation, that's sort of like multiplying both sides by dx. So you multiply this side by dx and multiply this by dx, they're all gone. Just lose all the dx's on the bottom, right? Multiply that by dx, multiply that by dx, just lose it. And it looks like this. The derivative of uv is u dv plus v du. Integrate both sides. Okay. Integrate. If you have the integral of a derivative, they cancel each other out. This is just uv. Integral of a sum is the sum of the integrals. Integral of u dv plus the integral of v du. Subtract on both sides, and there's the formula. Okay, so it is derivable. I know I went through that fast. You're not responsible for it, but at least I showed you, okay, my teacher kind of showed me where it came from. It comes from the product group. Okay, if you do the product group and you set it up the right way, it comes out to be this. You're not responsible for this. I'm responsible for this. Okay, if we were meeting face to face, I would go slower and actually try to make you understand much of it. But if you didn't get any of this, that's okay. Here's the formula. Just use it, so to speak. Integral of u dv equals uv minus integral of v du. So there's a formula. Put it on your cheat sheet. Not this cheat sheet. Again, not for this test. It's not going to be on this test, but the next test. Okay, so I'm just going to show you one example of it, and then I'll stop. Okay, here's the basic concept. Okay, so 7.1, number 1, integral of x squared, natural log of x dx. Okay, this is a product, something times something. Okay. I'm not sure if your Calc 1 teacher taught you this, but there's no such thing as a product rule for integrals. There's a product rule for derivatives, right? Here it is. First times the derivative of the second plus the second times the derivative of the first. Or maybe you had fg prime plus gf prime, right? There's no such thing as a product rule for integrals. So we have to do some tricks. Here's the trick we're doing. Integral of u dv is uv minus the integral of v du. Okay, here's the concept. From my original integral, I have to declare something to be the u part. I need something else to be the dv. Okay, it's not clear now at all. I'm going to transform it into something that looks like this. The whole idea is that hopefully this new integral is easier than this integral. Okay, so if you look at this integral, saying I don't like it, I don't know what to do. If I can make it look like this, and hopefully this integral is better. And by the way, I'm not really concerned about how complicated this is. This uv can have all kinds of weird stuff, exponentials, logs, square root, cube root, strange fraction. It doesn't matter. I'm not doing anything to it. I'm just writing it down. I'm not differentiating it. I'm not integrating it. I'm just writing uv. Okay, so number 1, integral of x squared ln x dx. So suppose I said, let u be ln x, dv is x squared dx. Okay, so if you temporarily ignore all this, I say u equals natural log of x, dv is x squared dx. So now it does look like u dv. Yes, you may say, how do you know to let that be u? How do you know that's not u and that's dv? Correct, we don't know yet. You'll learn later from some experience. Okay, so I'm going to try to transform this into this. So if I let u be that, dv be these two guys combined, I've got it to look like that. Now, here's one rule. Okay? The dv always has the dx, and the u just has x. So you never have the u with the dx, and you always have the dv with the dx. Okay, you always then differentiate this side, and you integrate this side. Okay, so this is diff, which stands for differentiate. This says int, which means integrate. Differentiate, integrate. So this says dv equals the integral of x squared dx. It's perfect for integration, right? And even the letters kind of match. Okay, differentiate. U equals ln x. Use the differential notation. Du equals 1 over x dx. Integrate. Integral of dv, that's at the integral of 1 dv, that's v. That's always going to be this step. Okay, this is never going to change. It's going to be the integral of dv is v. Integral of x squared is 1/3 x cubed. For this part, you don't have to put the plus c. No plus c right now. Now, notice I have 4 parts, which is why it's called integration by parts. I have my u, my v, du, and dv. Okay, so one more time. I declare u to be ln x. We don't know why it works. Just do it for now. dv is the rest of the stuff. dv is x squared dx. Okay, one thing is certain. The dv and the dx are always in the same equation. And this side doesn't have any d's. No du dx. So it does fit the rule of integral of u dv. Okay, differentiate this side. There it is. Integrate this side. Now I have a u, a v, a du, and a dv. Plug it into here. Okay, so by formula, u times v. So u times v is that times that. ln x times 1/3 x cubed. There it is, 1/3 x cubed ln x. That's my uv. U times v. That times that, 1/3 x cubed ln x minus the integral by formula v du. So v is that stuff, 1/3 x cubed. And then the du is 1 over x dx. So I multiply v times du. Takes a while to get used to this. Okay, v du, 1/3 x cubed, 1 over x. Okay, and now if you look at this integral, there's no more ln. It's going to be a simple polynomial. Okay, you say this looks pretty bad. It's pretty bad, but I'm not doing anything. I'm just writing it down. I don't have to differentiate this. I don't have to integrate it. See, the uv isn't part of any derivative. It isn't any part of an integral. So I'm not concerned about how bad that is. I'm just going to copy it down. Okay, now if I multiply these together, let's see, that's going to be 1/3 x squared. Do you agree? X cubed times 1 over x. So I'm bringing that up now. Okay, so bring that up over here. 1/3 x cubed ln x. 1/3 x cubed ln x. Minus integral of 1/3 x squared. Now this is an easy integral. Right? So leave this alone. That's going to be minus 1/3. Integral of x squared is x cubed over 3. This is now an indefinite integral, right? The previous chapter we almost did no indefinite integrals, just definite integrals. But now we are doing indefinite integrals, means you put the plus c. And just multiply it together. So here's the final answer. 1/3 x cubed natural log of x minus 1/9 x cubed plus c. So that's integration by parts. I was only going to show you one today. Okay. Yeah, you might feel kind of lost now, but at least you've seen it. So when I show you more Thursday, hopefully it's a little bit better. Believe it or not, if you try to take the derivative of this mess, if you do it the right way, by the way, that's going to be a product rule here, right? There's a product rule. That's just a polynomial. And of course, the derivative of a constant is 0. If you take the derivative and you do it the right way, what should you get? X squared ln x. Okay, so I'm done with the problem. I'm just going to dig a little bit deeper. Okay, suppose you had said, how about I'll let this be u and let this be dv, right? You have to declare some part to be u, some part to be dv. So let u be x squared, dv is ln x. U equals x squared, dv is ln x dx. Okay, technically that's correct, but you differentiate this side, you integrate this side. Okay, how do you integrate natural log of x? Careful, not the derivative. We know the derivative of ln x is 1 over x, but I want the antiderivative, the integral of ln x. Okay. Chances are your Calc 1 teacher didn't teach you integral of ln x. He wasn't part of it. Okay. We are going to get it. Okay. In fact, that's part of integration by parts, but we prefer not to integrate ln x. Okay. So I put that there. We prefer not to integrate ln x. We prefer to differentiate. We prefer not to integrate ln x. So one thing that tells us right away is if I see ln x in my integral, I don't want to integrate ln x. So that tells me I'd rather differentiate ln x. I know the derivative of ln x, 1 over x. So it looks like my first rule is if I see an ln x, let that be the u part, and the rest of the stuff is the dv. Now I see x squared. X squared is easy to differentiate. X squared is easy to integrate. That doesn't bother me either way. So we're fine with that. Okay, so I'm going to stop there. That's as much as I want to show you from today. So I'm finished with all of chapter 6. And so the coverage of the test was what I already showed you. So let me stop share right now and come over here.
Hey, Professor.
Yeah, let me say something real quick, Raishan. Sorry. But so, I'll show that to you again. But yeah, so chapter 6, sorry about that. Go back to sharing the screen. Yeah, so I'm finished with this. So you can start studying for the test next Tuesday. Thursday, I'll do more of 7.1, but that won't be on a test. And maybe next Tuesday, I'll sneak in some of 7.2 also. Okay. Yeah, Raishan, you had a question, please?
The eighth edition number 1 is different.
8th edition number 1 for 7.1.
Yeah.
Oh, okay. Probably same as before. Okay, so if that's the case, call it 7.1 star again. I guess what did they put? E to the x, e to the 2x? Yeah, okay. And I'm just wondering if that shows up, the one that I showed you, x squared ln x. It does not. Okay, well, sorry. Well, you learned something anyway. Okay, but I see that doesn't match. All right, but thank you for telling me. Okay, let me check the chat. Let's see. Okay, Chiali, I got it. You know, that happens to me sometimes, so that's fine. Okay, anybody want to ask me anything? Because if not, I don't mind stopping now. What is it, 9 o'clock-ish? Okay, and like I said, I was mean to you by making you go extra, so I don't mind stopping early because of that. Okay, let me check the chat again one more time quickly. Anything else that's there? So I think you mean the mean value theorem? Is that what you're talking about, Tiali? Okay, the mean value theorem for average value of a function. Okay, so let me see. Whoops. Share the screen, do this, do this, do this, do this. Okay. So the concept is if you have a continuous function for the average value, right? So here's the function, there's the average value, okay, by formula. That average value touches the curve. That's the mean value theorem. It has to happen at least once. It might happen twice. One of the problems I did was just like that. It happened twice, right? But if you have a continuous function, it has to happen at least once. That's what they mean by the letter C. That's what all of this is saying. So you find the average value. Okay, the average value touches the graph. That x value is called C. F of C equals the average value. Okay, so that's all. If you don't understand that fully, that's okay. Just throw it into the formula, essentially. Okay, or you can write that entire thing down on the test if you want. There is some C in there, and they might ask you to find the C. So that's all. Okay. Let's see. That's that. Okay, I think I'm caught up with the chat. And by the way, I know it's hard. You know how it is when you go up and down the chat, you can't read everything. So if I miss you, go ahead and type it again, or you can just unmute yourself and say it. Okay, but otherwise I'm done, folks. Anybody else with anything? Any questions? You can unmute or chat. No?
Can you explain the derivative of E during your timeout area?
Okay, that timeout thing again? Okay.
Yes.
So let me see if I can find it again. So that's part of the chain rule in reverse, right?
Yes, that one.
Okay, so maybe I'll make up some other thing here. So I'm making up new stuff here. What's the derivative of, let's say, I don't know, e to the 4x? It's e to the 4x times 4, chain rule, right? Because the chain rule said you leave this e alone, e to the 4x, but then you have to multiply by the derivative of 4x, which is 4. Okay, so if I differentiate it, I multiply by 4. Therefore, if I integrate, remember, integration and differentiation are opposite operations, right? So here, if I multiply by 4, what do you think happens here? You divide by 4, or multiply by 1/4. So that was a shortcut that I employed way over here. Okay. And likewise, I don't know, what's the derivative of cosine of 7x? What's the derivative? Negative sine 7x, sorry, that's a 7, times the derivative of 7x, 7. Right, so what happened? I multiplied by 7. Therefore, if I integrate, I would divide by 7 or multiply by 1/7. So the integral of cosine of 7x dx, integral of cosine is sine. And this time I don't multiply by 7, I multiply by 1/7. Like that. Just because integration and differentiation are opposite operations. Okay. And remember, the derivative of e to the x was e to the x. Okay. It's too much to go over the derivation of that. You saw some of that in Calc 1, hopefully. But just know what derivative of e to the x is e to the x. And if you have something like e to the 4x, chain rule. All right, so over here, cosine 7x, negative sine 7x times 7. So I took the original times 7. So when I integrate, it's not times 7, it's times 1/7. And that's what I was showing here. So over here, it looks like there was a pi/12t. So if I integrate, it's 12/pi. 12/pi t. Okay. Let's see.
Thank you.
All right, you're welcome. Michael Decker, can you send me an email, please? I'll get you. All right, let me check the chat here briefly. Yeah, if your Wi-Fi goes down, I get it. That happens to me sometimes. So, all right, anybody else, please? Check the chat. And yeah, Rayshawn, thank you for pointing that out, because that'll happen from time to time. I got to try to make sure that I coordinate there. Okay, I don't hear anybody, and I don't see anything in the chat. Anybody else? Okay, let's call it a night, folks. All right, that'll do it for tonight. So everybody, good night. I'll see you on Thursday, and test is next Tuesday, remember. Okay, all right, good night, everybody. Bye.
Peace out, Mr. Ron.
Thank you, good night.
Bye, Mr. Hom.
Bye, good night, everyone.
Yeah, Mr. Hong.
Bye, Mr. Hong.
Bye, Mr. Hong.
Bye, Mr.
Bye, Mr. Hong.
Bye.